The question that I have is, could you explain the nature of stress change in soil due to something like a footing loading? Supposing, say, we have a homogeneous horizontal layer of soil deposit consisting of a clay soil like this. Let's focus on the 2 points A and B. We know there's a vertical stress at point A and vertical stress at point B. Because these 2 points are at the same depth, these 2 vertical stresses would be the same, right? We already know how to calculate these, right? Remember summing up the gamma times H terms for all the soil layers lying above these 2 points, right? Now we're going to apply a column load and the stresses at these 2 points are going to change. These stresses, that is the stresses before the application of the column load, then serve as the initial stresses. We need to calculate these changes. Let's just say the change at point A is delta sigma 1 and change at point B is delta sigma 2. Now it turns out these 2 stresses are not going to be the same. How to calculate these changes is the subject here. Once we have these calculated, we know the final stresses at these 2 points. And these are the initial stresses, and then these are the final stresses. Why do we need to know these stress changes? Well, one of the primary reasons is that these stress changes will lead to settlement of the footings. And there are 2 types of settlements, elastic and consolidation settlements. We'll get into the details of these a little later, but for now, we need to be able to calculate the changes in stresses. We use footings of different shapes, circular, rectangular, strip, and sometimes irregularly shaped footings. We need to be able to calculate these changes for any of these footings. Loading, of course, comes in different forms. For example, an embankment loading like shown here. The weight of the embankment is going to lead to changes in stresses at these 2 points, and these changes will lead to settlement of the embankment, and to calculate the settlement, we need to know the values of these changes. In the earlier video, we talked about the stress at a certain point having several components, right? In a 2-dimensional plane strain analysis, at least there are 3 components, right? Vertical stress, horizontal stress, and a shear stress. So then you might ask, why am I just focusing only on the vertical stress? The answer to this question is that in these cases, that is, cases involving a footing loading or an embankment loading, the vertical settlement dominates over other components like horizontal movement and so on, and that the vertical settlement depends primarily on the changes in the vertical stresses. So here we will focus only on the calculation of the vertical stresses. Let's develop some qualitative understanding of the changes in vertical stress caused by a strip footing that applies a pressure of 100 kilopascal. Strip footing is one that is very long in the direction perpendicular to the paper. I have marked little differential elements at various points here. We'll try to understand what the magnitude of the vertical stress would be at these points in a qualitative sense. These 3 points are right beneath the footing, and it's pretty easy to understand that the vertical stresses on these elements would be exactly same as the footing pressure, which is 100 kilopascals. I'll just leave the units out just for clarity here. But as soon as you go outside the footing area, the vertical stress drops to 0 because this is a free surface. There is no stress acting on that surface, and therefore the vertical stress on this element, which is taken to be right on the surface, is 0. So there is a discontinuity at this point. This is what is called a singular point. The stress drops from 100 to 0 right at that point. What about the change in a vertical line like this? Well, the vertical stress decreases as you go down. Let's just say it is 80 over here and 40 over here. A similar trend is observed on a horizontal line. As you move horizontally from the center line, the stress decreases. Let's just say these are the values of the vertical stress on these elements, 80, 60, 40, and 10. You may want to note that while these 2 points are at the same depth, the vertical stress on this element is smaller than the vertical stress on this element because this element lies at a certain distance from the center line. Say we try to construct some contours here, that is, lines of constant vertical stress. We know the vertical stress on this interface, that is the interface between the footing and the soil, is 100 kilopascal. And therefore, that represents the contour of 100 kilopascal. And we see 40 over here and 40 over here, 40 over here. Therefore, a contour of 40 kilopascal would look something like this. I have drawn a couple more. This is a contour of 60 kilopascal, and this is a contour of 90 kilopascal. And one more. This is the contour of 10 kilopascal. So 10 kilopascal is only 10% of the applied footing pressure. So that tells us in this region, that is region outside this little bulb here, the changes in vertical stress is going to be less than 10%. These contours, shaped like bulbs, are called pressure bulbs. Now you have some idea of how the vertical stress changes in the soil mass right beneath a strip footing. The vertical stress change is localized in that it takes place in a region around the footing. Outside this region, the changes in stresses are negligible. I'd like to point out one more thing before we leave this slide. We noted that this is the contour of 90 kilopascal, right? This tells us that at points that are not too far from the plane where the footing pressure is applied, the pressure is going to be very close to 100 kilopascal. So these points, let's just say they don't exactly coincide with the plane where the footing pressure is applied, but it's still they're at a very small depth. As long as the depth is very small compared to the width of the footing, the change in the vertical stress can be approximated as 100 kilopascal, which is the footing pressure. There's one scenario where this type of approximation applies, and let's talk about that in the next slide. Supposing, say, we plan to build a high-rise building on this site. We find that there is a layer of clay in the site, which is estimated to lead to significant consolidation settlement. One way to minimize the settlement of the building is to do what is called preloading. Basically what you do is you bring a lot of soil from a borrow area, place it on the site, and let it sit there for a while. This will cause the settlement to occur before the building is built. Not all of it, but some of it. After leaving it for a while, you remove the fill and then go ahead and build the building. For the purpose of calculating the settlement caused by the fill material itself, we again need to calculate the changes in the vertical stresses at these points. Because the fill material covers a very large area, that depth of these points happen to be very small compared to the width, and therefore the changes in the vertical stress at these points can be approximated to be the pressure applied by the fill material, which in this particular example is 100 kilopascal.